Currently, my area of interest is electric vehicle technology and battery management system. Hello.
Yes, thank you, madam. Thank you.
Yeah. Yes, and I have executed 2 funded projects under DST, and we have electric vehicle technology center of excellence in our college, and we execute many funded projects in the area of electric field technology and battery management system. And also, I am very active IEEE member and also a faculty advisor for 2 IEEE student band chapters. Thank you.
Thank you, madam. Thank you. And next is Swami sir. Swami sir or madam, I don't know. Swami.
Hello.
Yeah. Yes, ma'am.
Hello.
Yeah. Yeah.
Good afternoon, sir.
Good afternoon.
Good afternoon, everyone. This is Soumya from NIT. Hello. Is it audible, sir?
Yes, it is audible.
Yes, sir. I am Soumya from NIT Meenakshi Institute of Technology, Bangalore. I am working as an assistant professor in artificial intelligence and data science, and I am pursuing my PhD. Completed my colloquium and thesis writing, about to submit. Another couple of months, I will be completing my defense. This is my research area is IoT with AI. And I am having 15 plus years of experience, sir.
Okay. Any publications so far?
Yes, sir. I am having 25 plus international journal publications and 6 plus Q2, Q3 publications till now.
Good. Congratulations.
Thank you, sir. Thank you, everyone.
Yes, Laure sir.
Yes, sir. Good
Yes, sir.
afternoon.
Good afternoon.
I'm Dr. Ajit Laure. I have completed my PhD from College of Engineering, Pune, COP, in the domain of sliding mode control. And currently, I'm working on the optimization of sliding mode control parameters for the process control system and motion control system. And I have published Scopus SI Index Journal about 20 plus and 4 conference papers. Thank you, sir. Thank you.
Yes, sir. Thank you. Thank you. Mahesh Raut. Mahesh Raut. Dr. Upendra Pal Singh.
Yes, good afternoon, sir.
Good afternoon, sir. How are you?
Well, fine, sir. Myself, Upendra Pal Singh, sir. I am currently working as a assistant professor in RVS Engineering Technical Campus, Bijpuri, Agra, UP. Now, behind 6 months before, I completed PhD from GLA University, Mathura.
Good. Good.
So now, sir, BTech completed in 2003 and MTech completed 2005. Now PhD completed in 2025, sir. During the PhD till now, the total 8 paper of 2 paper SCI and 6 scopers completed now and international and national conferences around 5. During
Yes, sir.
5 completed, sir. So now attended the several workshop, seminar, FDP focusing on latest solar photovoltaic systems. So my area is solar photovoltaic systems during maintenance, or my topic, that is the advanced practices of solar photovoltaic system during the predictive maintenance.
Okay, sir. Thank you. Thank you very much.
Thank you, sir. Thank you very much, sir.
Dr. K. Rajeshwari.
Hello, sir. Good afternoon.
Good afternoon, ma'am. How are you?
Yeah, I am from Pimpri-Chinchwad College of Engineering, sir. I serve as Dean Academics here, and
Oh.
I work as a professor in computer engineering. So I have started working with interdisciplinary domain. So control system is very new for me. I
Okay.
have a lot of publications, 100 plus, maybe in journals and conferences, maybe 1,500 citations and all. But I'm very new to control systems. Just wanted to learn something more to add on to my scholars. Thank you for the wonderful opportunity, sir.
Thank you very much, madam, for joining this. Rahul Dalandale. Rahul, can you hear me? Anita Kher. Anita, ma'am. Dhumar Sonali. Let us take this as an opportunity to interact with each other. Introduce yourself. Sonali Dhumar. Dr. Nalini.
Yes, sir. I'm
Yes,
there.
yeah.
Good evening, sir. This is Dr. Nalini Karchi. My domain is I have completed MTech in Control Systems from Walchand College of Sangli. And also my research area is also adaptive controller, design of adaptive controller for distributed generation. And right now I'm also working on the controller only, MPPT controller, inverter controller. And I have published around 22 papers in conferences, journals. Those are SCA, Q1, Web of Science, Scopus. I'm working in the college. The college name is KIIT Technological University, Dr. M.S. Sheshgiri, Campus Belgavi, since 2007. So this is like almost 20. I have a experience of 22 years in teaching field. Before I was in Maharashtra, but last 22 years I'm in Karnataka.
Okay.
Thank you, sir.
Thank you.
I'm also active IEEE member.
Good, good.
Okay. Thank you, sir.
Thank you. Thank you. Anita Kher. Shivalila. Can you hear me? Shivalila. Somebody joining with name Shivalila. Dhumala Sonali. Anand Kumar, can you hear me?
Yes, sir. Good afternoon, sir. My voice is coming.
Little louder, can you be?
Yes. Okay, sir. Good afternoon to all of you. I am Dr. Anand Kumar, and currently I am working as assistant professor in KKWIEER, Institute of Engineering Education and Research, Nashik. And I have completed my MTech and PhD both from NIT Patna in the year of 2017 and 2021. And I have published 5 journal papers, 3 SCI and the 2 scopus, and 3 conferences and 1 book chapter. And I have 5-year teaching experience. And before KKWIEER, I have working in the SVNIT Surat for 1 year, and before that NIT Hamirpur for 1 year. And my research area is mainly I have designed the various controller design for the power system analysis, and mainly we have designed the load frequency regulation controller design and the voltage regulations, and PIDA controllers, and the 2-degree freedom IMC controllers using the direct synthesis approach we have designed, and the sliding mode controller for the LFC systems. Thank you, sir.
Thank you, Anand. Meghnathan. Meghnathan.
Yes, sir.
Yes, sir.
Sir, myself is Dr. Meghnathan from Sri Manakula Vedayagar Engineering College, Puducherry.
Yeah.
I have completed my doctorate at 2024 in the field of solar photovoltaic system along with the power quality improvement. And I have published around 13 publications and 4 from Science Index and remaining are in Scopus. My current field is working towards an EV battery management system. Thank you.
Thank you, sir. Thank you. Dr. Nisha GK. Dr. Nisha. Dr. Vivekanandan. Dr. Vivekanandan. Can you hear me? Dr. Nisha. Himanshi Kodi. Himanshi Kodi. Dr. Raj Shekhar. Dr. Raj Shekhar. Iram Sheikh.
Yes, sir. Good afternoon, sir.
Good afternoon, ma'am.
I'm Iram Farhan Sheikh from Nasik. I'm working as an assistant professor in KIIT Engineering College and Research Center, Nasik. I have total 6 year experience in teaching field. I have completed my BE in from Gokhale Education Society RH Support College of Engineering in 2018 and completed my ME in 2020 from Matushi College of Engineering. My research area in solar system. I'm also researching in PhD on the topic of solar system also. And my total publication from during this teaching experience, total 9 paper, 1 IEEE Scopus, and 8 international journals, and 2 conferences. And total experience is teaching field 6 year. Thank you.
Thank you. Thank you, madam.
Thank you, sir.
Meenakshi S. Meenakshi S. Niharika. Please unmute yourself. Niharika. Richa Sharma.
Yes, sir.
Yeah, please introduce yourself. Richa Sharma, you are mute.
Sorry, sir.
Yeah.
My name is Richa Sharma. I'm working as an assistant professor at SGS ITS Indore, Sri Govindram Saxena Institute of Technology, in Electrical Engineering Department. Presently, I'm pursuing PhD. And I'm working in energy, renewable energy.
Okay, thank you. Niharika,
Thank you,
you
sir.
can unmute yourself and you can introduce. You are not audible. Remia Sukumar.
Good afternoon, sir. Can you hear me?
Yeah, I can hear you.
Sir, my name is Dr. Ilyas Prabharan. I'm working as assistant professor in Engineering College, Kottayam, which is located in Kerala.
Okay.
I completed my PhD from IIT Madras in the area in 2024 in the area of
You are not audible, madam. Remaya, madam.
and mainly I designed a model predictive control, sliding mode control, and a differential, which is prevented using a differential braking system. And I have 3 journal papers and
Hello, sir.
Yeah.
Hello.
Please go ahead, Niharika.
Yes, sir. Good afternoon, sir.
Good afternoon.
Hello.
Good afternoon. Go ahead.
I'm Niharika Behera. I'm from Karnataka. I'm a assistant professor working in BITM Ballari.
Okay. Are you pursuing PhD or have you completed PhD?
Yes, sir. I'm pursuing PhD in VLSI area, digital VLSI.
Okay. Okay. What made you to join this FDP? Are you working in control systems?
No, sir. I want to gain the knowledge because means through this FDP. I want to take knowledge.
Okay. Thank you. Dr. Raj Sekhar. Meenakshi S. Dr. Nisha GK. Dr. Nisha. Palani Vel. Yes. Palani Vel. You are not audible. Muthu Kumaran. Muthu Kumaran. Meenal Reddy. Meenal, can you hear me? Nikhilesh, Dr. Nikhilesh. Dr. Nikhilesh Pawar. Godfrey Daniel.
Yes, sir.
Yes, sir. Please introduce yourself. Godfrey Daniel.
Good afternoon, sir.
Good afternoon. Good afternoon.
Thank you, sir. Sam, I am Godfrey Daniel, sir. I am working as professor in Sri Manakula Vinayagar Engineering College, Puducherry.
Okay.
Control Engineering Department.
Have you completed PhD or pursuing PhD?
Can you hear me?
His voice is breaking.
So, no, sir. Not completed, sir.
Okay.
Only MTech, sir.
Which area you are working?
Sir, Sri Manakula Vinayagar Engineering College at Puducherry.
Okay.
Puducherry.
Okay. Thank you.
Okay.
Dr. Vivekanandan.
Yeah, good afternoon, sir. Am I audible?
Yes, sir, you are.
Yeah, good afternoon, sir. This is Vivekanandan. I am Associate Professor at PCCOE, Pimpri-Chinchwad College of Engineering, Pune. And I have 25 years experience in teaching and 2 years in industrial experience at Thermax, Pune. And I have completed my PhD, and presently I am working in the Azola plant, HVAC systems, heating, ventilation and air conditioning system. And my PhD area was in the area of designing a controller for anti-lock braking system for rough road conditions. So I have about more than 30 publications and around 8 to 9 in SCI, and others are in Scopus. So I joined this one to get more further information, what's happening latest. And I'm also working in a water flow system for aquatic conditions.
Okay.
So I'm trying to design a controller for that. With that hope, I have joined this course.
Okay, sir. Okay, thank you. Thank you.
Thank you very much. Thank you. Good day.
Dr. Abha Kumari. Dr. Abha Kumari. Can you hear me?
Sir, Palanivel, sir. Good afternoon, sir.
Good afternoon, sir.
Yeah, is it audible, sir, now?
Yes, it is audible.
Yeah, myself, Palanivel. I am working as assistant professor in NIT Meenakshi Institute of Technology. Now it became in NIT University in Bangalore.
Okay.
My research area is disease prediction in healthcare, sir.
Okay.
So I have 19 years of experience. I have more than 12 journals and conference about 25 papers. So to enhance my knowledge, I joined this meeting, sir. FDP.
Okay. Thank you.
Thank you very much, sir.
Anupam Kumar. Dr. Anupam Kumar. Anupam Kumar Roy. Anita Kher. Mr. Mahesh Pagar.
Yes, sir. Good afternoon. Myself, Mahesh Pagar. I am pursuing in MTech Power System, and my academic focus includes power quality improvement, renewable energy integration, and industrial automation technologies like PLC, SCADA, and IoT based systems. Along with academics, I am actively involved in education through Luminary Institute, where we work on guiding students academically and supporting their career development. I am particularly interested in research, innovation, and practical implementation of electrical engineering concepts. And I am glad to be part of this faculty development program to enhance my knowledge, interact with experts, and learn new advancements in the field. Thank you.
Thank you, Mahesh. Thank you.
Yes.
Porcelvi. Kritika Ingre. Nikhilesh Pawar. Himanshi Kori. Himanshi, can you hear me? Meenal Rade. Meenakshi S.
Sir, good afternoon, sir.
Good afternoon, ma'am.
Sir, good afternoon, sir. Myself, Meenakshi. I'm doing my PhD in KIIT College of Engineering under the guidance of Dr. Prabhakar. And my research domain is soft robotics and currently I am designing and fabricating the soft robotics, and hereafter we are planning to design a controller. So this FPT will I can gain more knowledge about advanced controllers. That's why I joined here, sir. Thank you.
Thank you, madam. Thank you. Porcelvi.
Sir?
Yeah. Please
Hello,
go ahead.
sir.
Yeah.
Sir, can you hear me? Sir, I'm currently working as a
Your voice is breaking.
Hello? Sir?
Hello.
Sir, can you hear me?
Yes.
Sir? I'm currently working as an assistant professor in the department.
Your voice is breaking. Your voice is breaking. Voice is not clear. Meenal, can you hear me?
Sir? Sir?
Yeah.
Sir? Can you hear me?
Madam, your voice is breaking.
Sir, can you hear me?
Sir,
I'm basically currently working as an assistant professor in the department of
Madam, there is a noise from your end.
Sir, can you hear me?
Please.
Currently, sir.
Yes, go ahead. Go ahead.
So, I have completed my, I have submitted my thesis in the area of power electronics. Sir, breaking. Sir.
Yes, go ahead.
So, I've joined this FPT in order to gain some knowledge about the advanced controllers.
Thank you. Thank you. Thank you. Thank you. Kritika Ingre. Anita Kher, madam, please. Unmute and introduce yourself.
Am I audible?
Yes, madam.
Good afternoon, sir. My name is Anita Kher. And I'm working as an assistant professor in Allard College of Engineering, Pune. I have completed my Masters of Electrical Engineering in Control System in 2019. And I have 4 years of experience in teaching field. My area of interests are machines and electric vehicle design. And also I have to enhance my knowledge in control system. So I got opportunity for this FDP. So thank you for this opportunity. And I have one Scopus Index International African Journal paper, and also I have one paper published in national conference in IoT based monitoring. Thank you.
Thank you, madam. Thank you.
Okay.
Dr. Abha Kumari, you can unmute yourself.
Thank you, sir. Good afternoon to all of
Good
you.
afternoon. Good afternoon.
Dr. Ava Kumari is here. I am assistant professor in MIT Muzaffarpur, Bihar, and my research area is model order reduction techniques and controller design optimization. And I have so many SCI journals paper in reputed journals such as IIT, Journal Research, and Circuit System and Signal Processing. That's all. Thank you.
Thank you, madam. Thank you. Somnath Hadpe. Can you hear me, Somnath ji? Who is left? Anybody interested can raise the hand so that I can unmute, or you can unmute on your end. Yes, anyone interested to share the area of interest, research? If not here, you can put in the chat box. You can write your details and area of interest so that people can read it. I think we have our next speaker here. Dr. Deep, you are there? Dr. Deep Mukherjee.
Yes, sir. Good afternoon.
Good afternoon, sir. Good afternoon. Good afternoon. How are you?
I'm fine, sir.
Okay. So we will start with this. I will request my colleague, Marine John, to provide the brief introduction of Dr. Deep Mukherjee, and then we can proceed with the session. Marine, are you there? Marine, your voice is not coming. Voice is not clear.
Hello. Sir,
Yes.
am I audible?
Yes, you are audible now.
Thank you respected participants, for your wonderful introduction. It was really encouraging to hear about the diverse expertise of the participants, and I sincerely hope that the connection made today will lead to a joint research or long-term professional relationship. Let's now move on to the next section of FDP. So let me introduce today's eminent speaker, Dr. Deep Mukherjee. Dr. Deep Mukherjee, Assistant Professor at School of Electronics Engineering, Kalinga Institute of Industrial Technology, deemed to be university. Dr. Mukherjee has rich academic and professional experience, including several years of teaching and industry exposure, and has been actively contributing to education and research in the field of control and instrumentation engineering. He holds a BE in Applied Electronics and Instrumentation Engineering from Buddhain University and an MTech in Instrumentation and Control Engineering from Calcutta University. His teaching areas include industrial automation and control, process control, control system, instrumentation, analog and digital electronics, and measurement system. He's a member of the Institution of Engineering and Technology, UK, and also serves as a reviewer of various corpus index journals. His research interests focus on fractional order controllers for non-linear processes, non-linear control strategies, and optimization technologies. He has presented his research work at several conferences and actively contributes to academic developments through workshops, seminars, accreditation activities, and conference organization. He's also been guiding undergraduate projects under his mentorship. Students have achieved recognition at various innovation competitions. Today, he will share his insights on fractional order controller. Please join me in warmly welcoming Dr. Deep Mukherjee to deliver his talk. Over to you, sir.
I am making you co-host so that you can share your slides. You are not audible.
Now am I audible?
Yes, now you are audible.
Okay. Thank you very much, Professor John, for a brief introduction. Good afternoon, all the participants present here. And thank you, my sincere thanks to Professor Dr. Mukherjee for giving me opportunity to connect all the participants, giving a talk on fractional order control in the 4th International Faculty Development Program on Advanced Topic on Control Systems. So I'm just about to share my screen. This screen is visible, sir? It is visible to...
It's coming. Everyone. It's coming. Now it is visible.
Okay. Okay. So today, basically my core research area on fractional order control, and this is the outline for today's talk. And in a nutshell, that I will put my discussion covering this following topics, and this is a very small part of my research work. So first of all, that I will be sharing my view that is on importance of the fractional order and how it is differentiated from integer order calculus methods, and why it is more popular than nowadays. Because this fractional order recently, since for several years, has gained a lot of more attention to all these experts and researchers due to its high ability, the control system modeling. Next, that to design the controller using the fractional order is a very difficult and challenging task. So there are many analytical techniques available. So I will stick on this first few techniques through which that it can be understood that how to solve this fractional order in the control design. And here that I have basically designed a lot of control topologies like model reference adaptive control, internal model control, cascaded PID control, using the fractional order. But I don't want to feel bored to the participants incorporating all these control topologies. So that's why I stick on these most emergent topics tools recently that I have developed. So that is a fractional order backstepping control topology. So backstepping control is the most emerging tool. And recently that it is the latest research that we have designed is using the fractional order. And we have applied this backstepping control on some mechanical under-actuated process like inverted pendulum and chemical reactor process, continuous reacting reactor process. So here that I will show you some is basic development designing and some results and simulation part. So that may conclude that backstepping control that outperforms these other topology schemes. So moving on this, first the difference, what is the basic difference? That's my view that integer calculus and this fractional order calculus. So integer order calculus basically, it basically it follows some local property. So local property, that means, that it depends on some neighborhood values, some nearby values around the function, around the point. Okay. So suppose that we have taken one function that y equal to x square, and if we would apply some first order and the second order derivatives, so that it shows the final outcomes. So it's like the straight line that is the nature of this first order, second order derivative that we have got it. But the thing is that integer order methods cannot fully capture the exact information, detailed information about this particular function or this process. Okay, so that is why it is more challenging. So that is why we have here. That is why the fractional order gains a lot of attention here, and because that if you see this equation, this function, so that is d to the power alpha ft. So if alpha is assumed is 1, so that means it's considered as an integer order method. But if alpha that if it lies between the 0 and 1, so it will be represented as the fractional order. Okay. And so basically this is the equation. Basically it is, so many techniques in the fractional calculus are available, like the GL method, that's the Grunwald-Lednikov methods, Raman level methods, Capito fractional differential methods. So this is the one derivation, that is the mathematical expression of RL fractional calculus methods. Okay. So here basically, that is a T. That is a T, basically it stores some the past value of information, and this T minus U, so that it's known as the memory weight. So it is basically fractional calculus. It basically depends on the non-local property. So non-local property means it stores some past value of information as well as the present and future states. Okay, it can represent. So that is why to store the past value, it requires the more memory elements. Okay, so that is known as the long-term memory effect. Okay, so that is the limitation that you can see of this fractional order calculus. But the advantage is that here that
जल्दी आओ, कैसे रो के आ रहे हो?
Okay, am I audible?
Yes, sir.
Yes,
sir,
yes.
You're
Okay,
audible.
yes, yes, something else. Okay, okay. So now that here that this is the graph shows the exact performance, detailed information, accurate information of this particular function. Okay, so here that alpha you can increase or decrease the value of alpha. So by increasing or decreasing the value, towards this one, by increasing the value, so you can here that observe that exact nature. Okay, so means past states of this particular function. Okay, right. Exact behavior, more details, accurate, how it transforms to the straight line. So that is not cleared that by the integer order methods. Okay, so that is basically maybe cleared by applying the fractional calculus. Okay, by increasing or decreasing the alpha, that is a fractional order. So that is why it is more flexible, unlike integer order calculus methods. Okay, so that is the main thing. That is the significant impact of this fractional order calculus over this integer order methods. Okay, and this is the common MATLAB generalized code that so one example that I have shown here. So using some in the under fractional calculus, some many functions like the beta function, gamma functions that are available. But that using that particular properties that we have here declared a common function. Okay, so using this common function, this code, we can pass any type of function and we can analyze the behavior of the different function, logarithmic function, exponential functions, whatever. Okay, so that is the main advantage of this fractional calculus of this integer order method. So that's why it becomes more popular, because it stores some past value information. It can give you the past results, exact more information that is details inaccurate. Okay, so now that thing is that if you suppose integer order, you are applying some integer order control in some nonlinear models or any other models, okay, systems models, and you are getting by applying this integer order control like PID control. So PID control means there are three parameters, tuning parameters are there. So like the KP, KI, and KD, there are three gains. Okay, so by using that particular tuning the parameters, by applying them optimization methods, so you are getting some response you are getting. Okay, some outcomes you are getting. So, but in these results, suppose you are getting some high overshoot, that becomes that response becomes so sluggish in nature. Okay, to track these particular points. Okay, so in that case, there is no scope of further improvement of this particular systems. Okay, that to make it, that is lower overshoot, that is to make that is to make more fastest response. Okay, so that is some lack is there. So overcome. So if you would apply some fractional calculus or fractional order control. So here the alpha is there, I mean pi to the power alpha and b to the power mu. So there are actually 5 parameters. So PID and alpha and mu. So there are 5 total parameters are there. So that is known, the alpha, that is known as extra degree of freedom. So by adding this extra degree of freedom, so you can tune more better. Okay, by increasing or decreasing, by altering the ranges in between 0 and 1, actually this is infinite range. Okay, there is infinite, that is a memory, so that is also to infinite. But our research that we have experienced that if you would put value that alpha between 0 and 1, so you'll be getting more stable outcomes, more handsome outputs that you will be getting. But if you choose the value alpha between 0 and 2 or from a higher order 0 and 3, whatever, so it might lead some oscillations in nature. So that is a restriction. Okay, so that is why it should correctly restricted, the value, the ranges of the alpha between 0 and 1. Okay, so by altering these parameters, this alpha or in another parameter beta, okay, the 2 additional degree of freedoms in the PID fractional PID controller. So then you can make lower the overshoots. Okay, so you can make the system more faster. Okay, faster, unlike the integer order calculus. Okay, methods that we have applied. Okay, so this is type of some merits, some advantages. So then we can achieve using this fractional, applying this fractional order control design. Okay, so but the thing is that whenever you will design the fractional order control, so you will be just you will be getting some fractional order transfer function, right? So by this fractional order transfer function in solving the MATLAB is very difficult task. Okay, so that is why it's a very common practice, that approximation to some any integer order is a very common practice. So that is why it is the fractional order term. So that should be approximated into integer order form. Okay, so it is a very common practice. So that would, because that is a otherwise that is a long time simulation, wrong run, because here infinite memories is there. Okay, so because more memory elements, so that means here that it requires more past value of information, so it runs for long time simulation in computationally expensive. Okay, so complexity is there, computationally complexity, so overcome it. So that is why this approximation is very necessary. Okay, so this approximation means that there are two types of approximations that is available. So one is that indirect approach, and another one is that direct approach. Okay, so indirect approach, if you find any research papers or any materials and use a fractional order control paper, so the maximum, most of the cases, so that is direct method has been applied. Okay, not the indirect methods. Why? This was the reason, because indirect methods, there are basically three types are there. One is the GL methods, that's a Gunnar-Politik of methods. One is that this Adel method, okay, Riemann-Little method, and another one is the Capito fractional differential methods. So they follow actually discretition rule. Means that this is the equation of GL method. So there is enter transfer function, fractional order transfer function, that term. So that should be transformed into the discrete step or any integer order approximation, okay, using some suitable mathematical analytical tools. Okay, so here this expression that is infinite series, so that is basically truncated into some n number elements, right? H is the step size. So that basically the accuracy that depends on this particular H and this n. So if you increase this value, to improve that accuracy, so then you have to, choose that proper step size and this n value. Okay, so by using that, you will be getting some more accurate results. Okay, so this alpha by k, so that is basically binomial coefficient that is represented in this way. Okay, or it can be expand in the series expansion, that is the series expansion from, so it is like that, suppose 1 plus x to the power alpha, so 1 plus x to the power alpha, so then 1 plus alpha x plus of alpha minus 1 by factorial 2 of x square plus so on. Okay, so this is the basically series expansion form actually. So now this truncated form, so that can be that is can be it should be mapped into some realizable filter. So now using some successive recursive approximation, recursive coefficient, okay, recursive coefficient, so then you can easily solve in the MATLAB. But the thing is that actually here, basically due to lack of some mathematical, algebraic mathematical equation reasoning, so this method actually, this indirect approach, it is not mostly preferred. So it might lead some approximation error. Okay, right. So that is why this indirect approach is basically it is avoided, and to approximate this fractional order. So that is another better alternative methods are there. So that is direct methods. So here the direct methods. Here the direct methods, that means that is that there are several methods are there, means it basically depends on frequency domain analysis. Indirect approach actually basically, indirect approach is basically for the time domain platforms. Okay, and but the direct approach basically depends on this frequency domain approach. Right. So frequency, there are three types of methods are there. One is the outslap. There is an outslap recursive filter approximation. This is the most popular method widely used in the many experts in many papers. There is the outslap recursive filter approximation technique. So this is the formula, because basically that here you have to transform in the fractional order. You have to approximate the fractional order solely. Means suppose this s to the power 0.4. Okay, so means from this equation, by Laplace transform and using some zero initial condition, okay, so you have to here that solely approximated, so this fractional order term, that is s to the power alpha, the sole approximation, okay, not the entire models. So here that we have here, for example, that we have chosen any arbitrary order like s to the power 0.4 to analyze this particular approximation techniques. Okay, so s to the power 0.4 that we have taken here, that is alpha equal to 0.4. By using this outslap recursive filter approximation, so this is the basic rational transfer function representation, where z is the gain, and that is the pole zero configuration, and n is the order. You have to first pick the order. Order means that is you are getting the first order, second order, third order. But there is a limitation in this model, is that is 2n plus 1. Means you depends on odd number of models. If you select n equals to 1, so n equals to 3, 2 means n equals to 5. So then it is we have here, for example, that for analysis that we have uses 2 orders. So one is that third order, and then is the fifth order approximation techniques. Okay, and here basically can mimic the frequency response. This approximation mimic the frequency response of this particular fractional order models. Okay, that is the magnitude and phase response. Okay, so now here that basically using this if you use there is a one tool is there, so that is the FormCon toolbox is available in the MATLAB. So that is the fractional order modeling and control toolbox. But the drawback of this toolbox is that in the toolbox only this outslap recursive filter, this approximation technique is available. That is a indirect method. Okay, but there is no option of applying some other approximation technique, because this technique does not give you the guaranteed that it will always give you the stable approximations. Okay, so that is the major issues. So here also that our objective is that to approximate the fractional order in the frequency response by showing the stable gain and no ripple and without ripple. Okay, so in the phase that we are getting some ripples is there, so that means it's not stable. Okay, right. But here also that we are the main thing is this this particular this direct method, the frequency band selection is very important, because the lower and high frequency band selection. So your accuracy that depends on this band selection. So you have the 100 and 0.01 that you have selected. So that selection is very important. Okay, so by selecting that, you know that you are getting some this approximation, but still that you are not a stable gain we are getting, and the ripple is there. So it's not a stable phase outcomes that we are not getting. So it's not a stable approximation. So here, though that in the third order, or if you increase the order, so you are getting some wide band gap, but use the decrease the orders, you are getting some narrow band gap. So that is the advantage that you can increase the higher order, approximation that that n equals to 5 for that you can apply it in this approximation, but it does not give you the guaranteed stable approximation. So we need to figure out any alternative method so that can replace this particular approximation technique to design the controller and to achieve more handsome outcomes. Okay. So here there's another for comparative analysis. So we have applied some continued fraction expansion. So that is CFE, that is method. Okay, so that method also can be applied, but it is comparative analysis using this, following this formula. So now there is recursive, that is rational transfer function. So that we are getting here the corresponding phase and amplitude response. So here also that we are getting the CFE fails to approximate it, because CFE in the phase response, it is a very narrow band gap. It's not a wide. Okay, but in the outslap recursive filter approximation, we have the wider band gap. Okay, so that is the one drawback that we are getting into the CFE, and also that it is not quite stable. Right, so that is why to achieve more better approximation, more stable outcome and continuous gain, stable gain. So we have now chosen, so that is the bichromatic equilateral approximation method in your research, because this is the open research, and this method has has not been applied in any papers and by any experts till now. It is still a novel method. Bichromatic equilateral rational approximation success, that is a recursive, that is the rational function. This rational transfer function is okay. So here, so here that here specific some coefficients are there, like the C1, C0, and C2. There some coefficients are there, and corresponding value that has been chosen here. So now the thing is that here the main some less ripples. Okay, so that is the less inner ripples, and there is the more outer ripples are there. Okay, but is the outer ripples. But in the CFE, if you compare with the CFE method, so here you are getting some more inner ripple, but it's a less outer ripples. Okay, so that is the comparative analysis that we have done here. And one more thing, major thing we have got, so that is this biquadratic equivalable approximation. Using this biquadratic that equivalable approximation methods. So here that we have got the wider band gap. Okay, unlike the CFE methods. Okay, so and here also that we are quite stable again, unlike the CFE methods, it has been attained by this particular outlier recursive, but it is not an end, because our objective was that to provide that more stable gain and ripple free, that is the phase approximation. There should be no ripples will be there. Okay, so there is that will be considered as the exact phase matching. Okay, so that is why that this technique has been modified by the biquadratic exact phase, that is a rational approximation technique. Okay, so this is the following conditions, and where that some corner frequency that has been chosen. Okay, so this omega c is the corner frequency. So this frequency selection, corner frequency is very important task and very challenging task to make stable. Okay, so that is the modified expression with the corner frequency rational function, and this is the correct parameter settings are given are there. So now that using this particular this equation rational functions, so we have got here the ripple-free phase examination. So this objective that we have achieved, so there is no ripples are there. So there is an exact phase match. But in the previous, this is the blue response. There is a blue response that shows the modified expression, modified methods approximation, and this red color that is the basically highlights that normal biquadratic equivalable. Okay, so where that we are getting some ripples. Okay, and using this modified expression that we are getting more stable gain, but here that it exact matches the pi by that is the pi by 5, that is the pi by precise and this steady phase approximation that we have attained. But the drawback is that one drawback also we are getting, we are basically narrow band. So this is not an end. Okay, so that means if you here we are use that is a one biquadratic transfer function, but you can here that incorporate with the second or third biquadratic transfer function. So that is the modular form. There is a cascaded manner. So if you would apply it, so this is under process that we are working on it. So if we apply it, so higher order transfer function, so then it can overcome this particular issue, and with no ripples, with no ripples. Okay, so but till now that we have achieved, as we have achieved this particular, we have eliminated these ripples. So now using this exact phase rational approximation is considered basically that most suitable and efficient alternative method that may replace that outlier recursive filter approximation or that CFE approximation. So we have designed our control topology so that using this particular exact phase rational approximation technique. And so here, first the topology that we have sticked on it, the best control here, because we have designed there are many topologies control, that is a model reference directive controls, fractional order based, internal model control, IMC control, and also PIPD cascade control systems, dual loop PIPD control systems. Okay, but here that we are strict on it backstrapping control, because just sharing that my work, that's our work is latest. This is our latest research work. So backstrapping control is basically the most emerging tool nowadays, and it is a one type of nonlinear control. Okay, so it used to stabilize stabilization for the intricate system. It's a more complex, systems that it might be more helpful to stability, because the main thing is that backstep. The backstep means steps backward. Okay, so means it steps backward from the inner subsystem. Means that suppose you have a model like any nonlinear model, so like that, for infrared pendulum models. Okay, so that is a nonlinear model. So this nonlinear model, so that should be, basically it is decomposed this particular in several cascaded straightforward subsystems. Okay, so this is the actually strict feedback system, a nonlinear model, so that should be transformed into the strict feedback form. Okay, so it follows the basically it recursive technique to stabilize the system. Backstepping control follows the recursive technique to stabilize the system using the strict feedback form. That is the most important thing. So you have to convert it into strict feedback form. So that is the each subsystem. So now you have got it. So suppose that is your first subsystem, that is your x1 dot, and this is your x2 dot subsystem. So the rule is that you have to stabilize each subsystem, okay, by introducing a proper Lyapunov function, right? So Lyapunov function that is basically used to stabilize the system, and that is the rule. Rule means that suppose x dot equal to fx, okay, so if you particular derivative that should be less than 0, so that it will be showing the global asymptotic stability. So each subsystem that need to be stabilized, okay, step by step from backward, okay, and until unless that final control law is achieved. Okay, so now that if you stable each subsystem, so entire system as a whole will be stable. Okay, so that is the main fundamental concept of this backstepping control. So here basically first that you have to here use basically that x1. So x1 basically is your first subsystem. So it need to be first, that is first system, and in first constant Lyapunov function like the v1 equals to half of that is not x1, right? So now you have to go for the derivative, and integer derivative is v1 dot. And if you would apply the fractional order, so that is very simple. So that is v1 dot to the power alpha. So then it will become the fractional order. Okay. So that by introducing by alpha, so it will be converted to the fractional order. So this is the first thing. That is you have to consider the Lyapunov function. Next thing that you have to design the virtual control. So virtual control law here basically that here in this expression, U is the main control that needs to be designed in the backstepping control. Okay. So virtual control law you have to design for the next subsystem. Okay, to make stabilize this first subsystem. So that is the rule. So that means you are using xi subsystem, means if I equals to 1, okay, so you have to design first, Lyapunov function, so that is equals to x1. Okay, so x1 equals to half. That is a Lyapunov function that you need to develop for the first subsystem. Okay, so now what you have to do, whenever you are using the virtual control law actually used to stabilize this subsystem, you have to design the virtual control law for this subsystem. Okay, so man, you have to use this virtual control law you have to introduce for the subsystem of this x2. Okay, for the subsystem of this x2 to stabilize of the x1. And so on, that you need to step by step that you have to proceed, okay, until unless your final control law that is achieved. Okay, so that is the basically the main concept of the backstepping control law. Okay, so now here that introduce basically the virtual control law. So first you need to define some the error tracking, the error variable of the second system. By now this was some my necessary arrangements and some simplification that you have to stable the previous subsystem. So again that you have to go for the next Lyapunov function, that is half x1 square plus half of x2 square plus so on. Okay, so if you would use some 3 and 4 subsystems, so it would be continued. So that is the main concept of this backstepping control here. So this is the main rule. So first you have to identify the system model. So then virtual control designs here. So next is the here that you have to design the particular Lyapunov function. You have to design it, and each step that you have to stabilize to make it globally. So ensure the negative definites of the derivative. Okay, so that should be less than 0. So then is the recursive design, you have to introduce the tracking error. Okay, so by necessity some arrangements and some simplification that was done, so to make the stable. So ultimately that you will be getting the final control law. So same thing that here your backstepping control that we have designed is a standalone methods. That is we have not incorporated any other control law. Simple standalone backstepping control that we have applied on inverted pendulum. And here that we have focused on particular angular position, because inverted pendulum we know that highly unstable in nature, and make it upright position, 0 position is very difficult and challenging task. Okay, so backstepping control, that is the efficient alternative that we have achieved, so that to make it more stable. Okay, and we have get more handsome outcomes. So this is Z1 and Z2, that is subsystem. So this is the particular nonlinear models. These nonlinear models, you have to define the subsystem. So there is a state variables you have to represent to design the backstepping law. So that is y equals to phi and y2 equals to phi dot to the power alpha here. So basically now this this subsystem. So after identifying this particular state variable, so the state equation like comes. So that is equals to y1 dot that is equals to function y2, and that is a y2 dot. So that is equals to function of, that is a y1, y2 plus of g of y1 and u. Okay, so here basically this is the basically kinematic form. This first row y1 dot, that is equals to y2, is a derivative, is a final kinematic form, and this second term basically isolates the nonlinear drift and this gain. Okay, so this is the nonlinear drift and gain, and u is the actual control input that need to be designed. Okay, so first subsystem, so that need to be stabilized first. Okay, so then followed by the second subsystem. So you have to here use the two Lyapunov functions. So first v1 that we have here considered in the same rule. By following the rules, here that we have shown the step by step the design methods. The backstepping controller that we have designed this subsystem z1 equals to y1, and followed by that we have construct this Lyapunov function v1 equals to half z1 squared, this corresponding this fractional derivative because alpha is there. So that is the this expression that we have got it. So now that you have introduced the error, because you have to compute the virtual control law. Okay, so this is the particular error function, and this y1 is the virtual control. So by this substituting some necessary arrangements and this simplification, that we need to stabilize the first subsystem, that is z1. Okay, so that it should be less than 0. So it should follow this particular criteria of this Lyapunov function criteria. Okay, so that is the particular criteria that of the global asymptotic stability. So after that, then you have to introduce move for the second subsystem. So you have to introduce the second Lyapunov function. So that is half z1 squared plus half z2 squares. Okay. Similarly, that you have to define the second subsystem to make it stable. So that is the particular law. Okay. So now that by necessary substitution here, the parameters that we have here finally control this achieved this control. So that is the u that is known as the final virtual input. So it is known as a backstepping law. This is a backstepping law because this is two subsystems that we are here incorporated in your bus. If you were to apply some 3-4 subsystems, so it continue. Okay, so unless that this final control law is achieved, so you have to move step by step and from this step backward from stabilizing that each subsystem by ensuring that it has a global stability, that your entire model that is stable. Okay, so that is the final control law. So by in this using this particular this expression that we have is a mathematical simulation that we have performed in the MATLAB, and this corresponding the result analysis that I am just sharing. So that is the significant impact of this fractional order control over this conventional method of control and some other conventional or fractional control topologies. So here basically that exact phase approximation technique is used to solve this particular fractional order backstepping methods. Okay, so basically that here the sole approximation has been done. So that we have discussed just I have shown the direct methods. So here that in randomly that we have actually by trial and error method that we have chosen the approximation value that may be 0.4, 0.8, and 0.6 the fractional order. But here we have not applied in optimization technique, but it is research is going on. It is under process. There will be next word that will apply the optimization technique. So here the first to observe the performance of this backstepping control, how it works and how it performs the other scheme. So we have just randomly have chosen the fractional order 0.6, 0.8. And among this, by this we have chosen their appropriate fractional order by looking into their performance study, their time domain and frequency domain analysis. So here that we have chosen the fractional order 0.4. So using this fractional order 0.4 here that we have some observe the response performance of conventional backstepping and fractional order backstepping methods. So basically we have started from a initial angular position randomly 0.4 and 0.167 randomly that we have given the angular position, and our objective is to make the position in the system is a stable to upright position, that is a 0. So here we have got some conventional and both method and conventional backstepping or the fractional order backstepping successfully tracks this 0 position, but it becomes sluggish when it takes up more time to reach that particular upright position. But unlike this fractional order that quickly settles at this 0 position, okay, by changing randomly the angular position. So here there's one point that we have got the fractional order backstepping. It's outperformed the CV. So we have moved on several analyses by applying this load disturbance and a time t equal to 4 seconds duration that we have done. So we have observed their efficient, effectiveness of this particular topology over this conventional backstepping methods. Here we can see that it is quickly settles in the particular zero position, unlike the conventional backstepping methods. Here we are introduced some the noise, and we have here some applied some saturation limit in presence of noise. So here that we can observe, we have observed that in this fractional order control effort, it is a very more stable, control output, and no such oscillations that we are getting here, unlike these conventional backstepping methods. Okay, and in case of this is another important measurement that we have done. So that is at 4 second time, we can give 4 seconds that we have applied sudden impulse at 0.3 radians. Okay, so it starts from 0.4 and suddenly that it applies some 0.3 radians. So despite having this sudden impulse, 0.3 radian, still this you can notice in the fractional order control, effectively tracks this particular position, zero position. Okay, without any too much no oscillations. Okay, so now that this is the most handsome outcomes that we are getting using the fractional order methods, backstepping methods, and here also that we have changed applied some value of the mass of the pendulums. So we have tested the robustness of this fractional order backstepping here in incorporating with this sudden impulse at 0.3 rad. Okay, so now that we have here, their comparative study has been done. So this is our previous works, so that we have published in papers, and we have applied fractional order model reference adaptive control in the pendulum models. So particular that tuning parameters that we have utilized on these models, and here that we have applied fractional order backstepping methods. So if you see the outputs in presence of noise and this nominal control efforts, this proposed fractional order backstepping methods outperforms the other scheme. They're providing that robust noise rejection. There is a robust noise rejection, not too much oscillations. Is there more stable outcomes that we are getting is the fractional order backstepping methods. Okay, so that is why in this controller the settings that has been given, and this control strategies and corresponding this performance metrics and control outcome, total variation, the value but parameters that has been we have measured, and this analysis that it proves that this proposed fractional order backstepping that under disturbance or for the product system that is outperforms. Okay, in terms of this less performance metrics and less error and this less total variation. Okay, so that is the that outcome that we have got throughout this analysis. So then we can analyze this proposed FOB that is considered as a most efficient alternative topology that may stable this mechanical under-actuated process. For example, here in pendulum that we have used, so that is more stable. Use other than other topologies like fractional order model reference adaptive control, or that we have actually compared with the standalone methods, and other is the dual method augmented techniques. Okay, that is a fractional order model reference adaptive control that is incorporated with the 2 degree of freedom of fractional order PI controller methods, and this is the standalone method, the normal fractional order low method that is falls under the category of model reference adaptive control, because there are 2 rules is there. One is the mid rule and it is the low cost stability rules. And through the analysis that we have basically observed that low cost stability basically outperforms these mid rules, because mid rules does not give you the inherent stability of the process. Okay, so that we have experienced on this particular nonlinear systems. Okay, so similarly that this by applying this FOB, we have designed for this continuous tank reactor models, CSTR models. So that is basically tri-states based system. There is a height, concentration, and temperature is there. So here my objective is that to basically track the concentration desired level So here the similarly same procedure is the backstepping techniques that we have. First, this nonlinear transfer function that will be transformed into the strict feedback system. Okay, and then again that it follows the recursive techniques. So you have to introduce some the virtual control law. Okay, so here the designing step by step that we have developed. Flowchart has been highlighted here. So you have to select first the control variables, then you have to introduce some errors. Okay, so by using some necessary substitution and simplification, that you have to stable the first system, then first system. Okay, so then you have to move for the second subsystem for the stabilization. So here the first subsystem that we have here includes the lower function. So by introducing this particular, by getting this the fractional order derivative, which is coming that this less than 0, so this negative is come, so that means it shows that global asymptotic stability. So like the inverted pendulum that we have done, the procedures that we have applied for the CSTR process, and here that ultimately that we have designed this particular fractional order stability law. So it steps backward from the inner subsystem, and each subsystem is stabilized by introducing the virtual control law and error brackets. Okay, and you have to introduce the particular low function to make sure that the global asymptotic stability, so that the whole entire models that will become more stable. Okay, so that is the main fundamental concept of this backstepping topology. So fractional order backstepping topology. So fractional order means that we have just introduced that is a particular extra degree of freedom, so additional degree of freedom, so that is the alpha. That's all. Okay, so now that you have to solve this Persson-Soul approximation, you have to solve using the biquadratic equitable, or you can solve in the Outslab-Dickert approximation. But what I have experienced, that I have shown that here, that biquadratic equitable, that is the more better alternative methods, that may that less than Outslab-Dickert. So because it provides some more stable approximation. So that is why that this method can be applied. Okay. So now this again, I have highlighted some responses, few responses that is to showcase the significant impact of this particular fractional order backstepping over the conventional backstepping and other fractional order control topology in the existing works. So here the desired concentration level. So suppose that we have put here some 1 or 0.867. Okay, so different concentration level. This is a 1 and this is the 0.867. Different concentration level that we have applied here. So accordingly that we have here observed the significant impact of the FP compared to the CB, because you can see the conventional backstepping takes more time to settle, to track this concentration, where this fractional order backstepping, fractional order backstepping, settles this particular, tracks this particular concentration. Okay, with the first settling time. Okay, and also that we are getting in the throughout this response, we are getting the no overshoot in the conventional or fractional order backstepping. So this is the one positive side. So this fractional order backstepping, so 0 overshoot that we are getting here. Okay, but sometimes that you are getting, you might not start from the 0. That is the initial condition, because due to some nonlinear nature, nonlinear effect, so it might start from these points. So that is why you have experienced due to some nonlinear effects. But we should be focused on the long-term dependency, actually, long-term stability, okay, rather than focusing on this particular point. This is not an issue that we have experienced. Okay, so it may start because due to some nonlinear effect, because we are handling some of the nonlinear models and tri-state models. Okay, so that is why. So the response will start from this point. Okay. So here that nominal and part conditions. So here that we have some experience. We have got experience using this, applying this by changing the parameters of the CSTR parameters. So internal parameters by changing. We have here analyze their robust performance. Okay, so still that it follows this particular track and concentration level in spite of changing the parameters. Okay, so that is why we have attained this particular performance through the fractional order backstepping methods. And here also that we have introduced some noise here. We introduce the noise, and it shows that it's robust to noise rejection process, the fractional order backstepping. And we have compared with this fractional backstepping that with some existing work, some FOPID by one experts, and our works, that is the FOLOI, FOPID, that is the augmented methods, that is the FOPID with FOMRSC augmented techniques. So whatever that under the we have observed this particular server already options and outputs and this input control efforts. So we have concluded this proposed FOP that is more swiftly and gracefully tracks these particular consideration. Okay, and in spite of the giving some load disturbance and introducing some noise. Okay, some noise, whatever. So then it shows the most robust noise rejection process and more stable outcomes and some outcomes that we are getting with less performance error, performance integral error, square matrix error, absolute term and absolute errors that we have got this value. So this value is very minimum and is a lower value. So we are getting than the other control topologies. Okay, and TV variation, total variation, the control output, so that we have also found. Okay, so throughout this analysis, so then we can basically conclude that the fractional order testing that it shows that no overshoot and it's robust servo noise rejection, high speed of connection, and lowest value of error matrix and smoothest control efforts. Okay, so that is all about my work. I am just shared with the participants, and hopefully that, as this is the backstepping method, is a very emerging tool, and I hope that some many research scholars and MTech participants, presence here in this program. So I think that this work, this particular kind of topology that might be helpful in their work if you want to apply this particular topology, these techniques on your models on systems. So I think that you might get some better outcomes, so you can do some comparative analysis. Okay, so you can try for that with these techniques. And this is the course references, so that we have actually followed and some tuning parameters of these polynomials and this computer pattern vector process, some the theory of this lower knob stability and some backstepping approximation technique. Okay, so that has been highlighted here. So if any question that you can ask me, so that is to my work that I am concluding it. And this is my contact, and if you have any questions further, if you have any doubts, so you can feel free to contact me, because you can collaborate me. So I'll be very happy to work with you, to interact with you. You can mail me. This is my WhatsApp and mobile contact number, so you can contact me anytime. So I'll be happy to interact with you. Thank you very much.
Thank you so much, sir. If participants are having some questions, you can raise your hands. You can unmute yourself and ask the questions. Or you can give the question in the chat box.
Hello.
Yes, sir. Please proceed.
Am I audible, ma'am?
Yes, sir. Yes, sir. Please proceed.
Sir, as per your opinion and as per your experience in the fractional order control system,
yes,
there are so many combinations are there, like integer order controller, integer order plant. Okay, integer order plant, fractional order controller, or fractional order plant or integer order controller. So as per your experience, which combination gives you the best result?
So you can apply the here that we have. You are asking about the fractional order model, right? You are about the fractional order model. You are asking about that.
No. I'm asking, sir, if a plant it is there and controller is there, right? Both controller and plant, they are integer order. Maybe possible possibility it is there.
Is there control integer order? Yes.
Yeah, and controller it may be the fractional order, while plant it is integer order.
Integer
or reverse of that it may possible over there. So which combination gives you the best result?
Combination basically that we have worked on still now, that is the fractional order controller on the integer order plant. Okay, so in this combination that we have worked on and we have got this response, this efficacy level, this fractional order control law. Okay, so but you can apply that fractional order transfer function, integer order transfer function that can be transferred in the fractional order models. Okay, so I think that if you apply some fractional order control with some fractional order models, okay, so you go for this combination. So I think that it is possible, but we have to need more about, more find out better approximation techniques. Okay, direct, indirect methods. Okay, so I think that from my opinion, according to me, that we have got experience that till now that we have used some integer order models. There is a simple plant, any models that can take it, and we are applying simply the integer order model controller that is the modified with the fractional order. So fractional order control, integer order model, fractional order control, integer order model. So I think that it would be the better combination to analyze it.
Yes, sir. Yes. Thank you. Thank you.
Thank you, sir.
Hello, sir.
Yes,
Hello.
ma'am. Yes, ma'am. You're audible.
Myself, Nalini Karchi. Sir, I have one question.
Tell me.
What are the real-time implementation difficulties of this fractional order controller? Real-time, I'm asking, sir.
Real-time implementation. Real-time implementation. Real-time implementation means, see here that we have solved these the fractional order control techniques. Fractional order, fraction into different fractional order control techniques like the direct and indirect methods. Okay, so basically that from my opinion, so we have faced till now that direct method actually basically direct method is basically mostly preferred. Okay, because if you put in a real time, suppose entire models, entire transfer function models. So entire transfer function models means then you have to transform into discrete form. You have to it should be truncated from infinite memory to n series elements. So now that you have to look for the accuracy, because you have to look for the step size and whatever things. Okay, so these things, there's complexity, these parts and maybe might be coming in this case. So that is a long time simulation. There is a long time simulation. Okay, there is a long time simulation. It is a computational complexity is there. Okay, so that is why this fractional order approximation, if you solely approximate, that is suppose s to the power function, this only approximated to, and it is converted to the rational transfer function model, suitable integer order form that you are giving, so that you can get some better approximation process. Okay, better approximation, and it would be easier to implement. But if you use some rational transfer function model, okay, so that will save that your particular times, and so that just you have to look on the frequency bandgap selection. Okay, by lower and higher order frequency bandgap selection real time, so then you can approximate the particular fractional order. Okay, so in this way that we can think it.
Thank you so much, sir. I hope we can wind up this session right now. Sir, thank you so much, Dr. Deep Mukherjee, for that highly insightful and engaging talk on fractional order controller. That was a very clear explanation of advanced concepts with practical relevance and research perspective.
Yes.
Over to you, the next session. I think we have our next expert join the session, Dr. Sunil Kumar Mishra. Dr. Sunil Kumar Mishra, sir, are you available?
Yes, madam.
Okay. Okay, thank you so much. Sir, we will move on to the session. Good afternoon once again. It's my great pleasure to introduce our next distinguished speaker, Dr. Sunil Kumar Mishra, Assistant Professor in Department of Electrical Engineering at National Institute of Technology, Silchar, Assam. Dr. Mishra has more than 8 years of teaching and research experience in the field of control system and renewable energy applications. He obtained his PhD in electrical engineering from Motilal Nehru National Institute of Technology, Allahabad, and has made significant research contributions in linear and non-linear control, artificial intelligence applications in control engineering and renewable energy system, particularly ocean energy conversion system. Dr. Mishra has published over 50 research papers in reputed SEI and Scopus Index journals and conferences, authored a Springer published book, and successfully served as a principal investigator of DST sponsored research project. His academic and research contributions continue to inspire young researchers and academicians in the field of advanced control engineering. Today, he will deliver a talk on nonlinear control strategies for ocean wave energy conversion system. We are honored to have him with us and are confident that his session will provide valuable insight for all the participants. I warmly welcome Dr. Sunil Kumar Mishra to begin this session. Please, sir.
Thank you, madam, for introducing me. Am I audible properly? First, I want to know.
Yes, sir. Yes, sir. You're perfect.
Okay. And one more thing, just I want to mention here that I have joined using two devices because I have joined this whole slides, everything from my PC, and another device I'm using just for video, so that all of you can see me also. And later on, actually, I'll be showing some simulation results, so that is actually better in PC. So as I have already been introduced, that my area of research is ocean wave energy and its controller design. So here, first of all, let me just give overview that how I'm going to cover this, because all of us are faculties and at the same age group. So it's just a sharing of knowledge. So first of all, I would like to introduce about the area in first 20-25 minutes. Then I'll be having second slide that will be covering that how we can design controller for this ocean wave energy system. And in the third part, in last 30 minutes, I would like to give some idea that how we can do Simulink design, all those things, and some other resources I would like to present in the later phase. So let me share my first slide that is for overview of this area. Okay. So I hope my screen is visible to everyone.
Yes, sir. Yes, sir.
So let's start. First of all, I'm very thankful to the Institute functionaries and especially Dr. Ravindra for inviting me for this lecture and for giving me this opportunity. This is the detailed outline of my presentation, first part of my presentation, where I will be introducing this area, that is ocean wave energy. Then actually main objective over here is to convert ocean wave energy into electrical energy. So for that, over a period of last 40-50 years, in fact 60-70 years also you can say, many techniques have been developed. So I'll be giving some brief overview. I'm not working on all techniques. I'm mainly working on this oscillating water column, but other techniques are also there where some pilot projects are running. So just to give a complete picture, I would introduce all these techniques. Then I'll be coming more specifically towards oscillating water column and its integration with Wells turbine and generators. So here mainly what are the components of oscillating water column and like how this technique works, I'll be discussing in this part. Then OWC control methods, like how many control, there are mainly two control methods, rotational speed control and airflow control. Those things will be discussed. And that just summarize this part, and then what are the future prospects available in this area, I'll be highlighting. Then this part will be over. Okay, so as we know that renewable energy is actually the need of the day. See, the most important thing is actually that fossil fuels are limited, and also when we use fossil fuels, the kind of chemicals that are actually released in the environment have a lot of problem for our climate, like global warming, and also pollution of the air that creates many problems like lung problems, all those things. So it is very important to include as much as possible renewable energy sources. So with this motivation, I started working in this area, same like other areas like solar energy and wind energy and any other like geothermal energy, tidal energy. I explored this area, ocean wave energy, and mainly from my PhD time, I started working on this. I did PhD thesis on this. So this area is not very new actually. It is very old, but the kind of investment that was needed in this area has been very less. So that is why still we are talking, we are in the early stage of development in this area. But this ocean wave energy is also very significant. How we can say that this is very significant? Because we know that the oceans cover almost 70% of the Earth's surface, and they are all like country like ours, India, which has almost 2/3 of coastal area. Means from three sides we have coastal lines. So if supposedly some small plants are just installed in this coastal line, and those are able to store and supply energy for local needs, so it can complement other energy sources very much, and the demand for other energy sources can be lowered significantly. So that is why this is very important, because and also it is available free of cost. Only problem is actually conversion. Like the conversion technologies needs to be developed, and high-end technology basically we need for in terms of structure, in terms of conversion process, in terms of basically controller, all those things. So, but the most important thing, it is clean and eco-friendly. So, and it is free of cost. Now, when we talk about history, so basically wave energy concept was earlier also. Like waves were used for different kinds of purposes. But first, this technology like oscillating water column was developed in 1966. Now here, this was just used as a floating buoy for lighting the lamps when seas were ships were navigating through oceans. So the small turbines columns were used actually, oscillating water columns, which were used to drive the turbines, small turbines to light the lamps. So those lamps were used for lighting purpose inside the ship. So it was very old concept. Later, this concept was used in seashore to just convert sea wave energy into electrical energy. And then after that, if you just scroll internet and search oscillating water column pilot projects in the internet, so you'll find so many pilot projects running in throughout the world. Here you can see these names like UK, Portugal, Spain, Australia. In fact, our country also had one oscillating water column power plant, which was installed in 1991 in Thiruvananthapuram, Kerala. Like it was there for since 2010, but after that, because it completed its lifetime and there was no further investment in this area, so because of that, this was decommissioned in 2010. More recently, one professor in IIT Madras is also working, Professor Abdus Samad, who is also working in this area, ocean wave energy. And he has tied up with some private company also for making the prototype and deploying in the sea. So many, all over world, many pilot projects are there. Some are at the commercial level, some are at the at the level of the pre-commercial level, and some are pilot projects only. But full commercialization of this is still awaiting actually. The reason is very simple, because right now we are more busy in exploiting solar energy and wind energy. Means the other sources are also, there is a lot of scope in those resources also. So like when those resources are saturated, that now this much we can only build the plants. So then we will move towards other resources like wave energy. So maybe in next 10-20 years, this area will also get more focus. But in the meantime, what is the role of researchers? The role of researchers is to continuously work in this area, so that you see, I'm just talking from the perspective of our country. like we should not lag behind in technology understanding and some IPR related things. If we do not work properly in this area, then other countries like European countries are still working very much in this area. Other countries like Australia, Spain, in fact, China, South Korea, all these countries have their wave energy program. So I have also tried from my side to get some research funded projects, and thankfully in 2023 I got one DST funded project in this area that has been concluded recently. It was in KIIT University of Bhubaneswar, where I was working till December 2025. Recently I have joined NIT Silchar. So it is very much required to work in this area. Now, coming to the types of wave energy converters, there are many types of wave energy converters, namely point absorber, attenuator, oscillating wave surge converter, overtopping devices, oscillating water column, and other kind of devices. So let me just give brief overview of these devices, and then I will move towards my area. So first, very popular, it is very popular actually, point absorber. So if we see this, how this converts actually into electrical energy, you see this actually represents the C waves. I just want to confirm, am I audible properly and understandable to everyone?
Yes, sir, you're audible.
Okay, thank you, madam. Okay, so here you see this is the just representation of the wave. So when waves actually come, there is a floating buoy which goes up and down, and here it is connected with a piston, and it is a kind of linear cylinder. So here it is directly connected to a linear generator. So that generator directly generates electricity. This is one way, or it may also be connected to a hydraulic, which converts linear motion into rotatory motion. So that can be also done. Based on that, when waves keeps on coming and this float goes up and down, and based on that, electrical energy is generated. Obviously, it will be fluctuating energy, but this is one of the technique that is there for just converting into electrical energy. Later, that energy can be through power converters. All those things can be smoothened out and can be stored somewhere, and then later it can be used. So this is one technique, and this is one of the practical example of this technique, point absorber device. So here you see. This part is actually a linear generator part, and the top part is actually floating buoy part. So and the company name is actually the device name is Power Buoy, and it was developed by Ocean Power Technologies. So let us move to another technique which is available. So this is called actually attenuators. So these attenuators actually again have joints. So these are actually different tubes. So these tubes are connected together through, and in the middle we have some power conversion modules. So when waves travel, and these are actually tied from seabed. You see these lines are actually tied to seabed, so that it is it does not go away just from the flow of waves. So here you see when the waves come, so these tubes will move up and down. So based on that, these hydraulic systems will have some differential, and based on that differential, some potential will be generated and electrical current will flow. So together all these are connected, and then this power is actually generated, power is taken out. So this is another technique called attenuators. So here this is the real example of attenuator called Philamis wave energy converter. It is also is the name of the company. So this company developed this wave energy converter, which is based on this attenuation concept. Now, next is actually oscillating wave surge converters. So here if we see, we can see this, we have a flap, which is actually again just, it is not very far from the seashore, very close to seashore. So here we can see that this is just fixed at seabed, and this flap moves just as per the direction of the waves. Suppose wave is coming from this side to this side, so it will go to that side, and then again it will recede to this side. So based on that, it is connected to a hydraulic, this pump, and this will actually this hydraulic will convert this linear motion into means flap motion into a rotatory motion, and then that will drive the generator. And then this generator is connected, means it will generate some electrical energy which can be taken out. So this technique is called actually oscillating wave surge converters. This is another device, actual device, wave roller, which was developed by AW Energy, and this is the animated diagram of this wave roller. I could not find the real picture, so I just used this animated diagram. So this is the flap actually, which moves like this, and here we have some motor connected, and this is the wire actually which goes to the grid. So this is the technique called oscillating wave surge converter device. Then we have another technique which is kind of semi-hydro energy, like where water is actually used to drive the turbine. So we also call it as hydro turbine or hydropower. So what happens actually here? So some ramp type of structure is made. So when waves strike to this ramp, because we have some wave height and coming up and down. So based on that, what happens here? This reservoir is filled, and then this reservoir is having some cavity, and in that cavity, some turbine generator system is set up. So that in that cavity, this water, means the water pressure is applied, and based on that, this water flows out from this direction, and this turbine is driven. When this turbine is driven, actually this generator is also driven, and based on that, electrical energy is generated. So we can see that this turbine is driven based on the concept of hydro energy or some hydropower plants. So basically here wave energy, through using waves, the water is filled in this reservoir, and then this water actually drives this turbine generator system. So we also have some companies like Wave Dragon, which is using this concept. Okay, this is the name of the device and also name of the company. Now coming to this another very popular technique, very popular actually, called oscillating water column. So now when we talk about oscillating water column, so what is column over here? So you can see that the column is a 4-walled chamber or cylindrical chamber, which is closed from all sides and open at the bottom. And at the top, maybe like this or like this also, turbine generator setup can be connected. So at the top, turbine generator setup is connected, and this turbine is not here. This time, this turbine is not like this hydro turbine. It is air turbine, like wind turbine. So this turbine is driven like this. Suppose waves are coming from this side, so they strike at the bottom of this column. So the water level, it is actually partially filled. So water level over here will move. When this water level moves, what happens here? Electrical energy. I'm sorry. Here the air pressure is actually varied. So when we have variable air pressure, this will drive this turbine, and then based on that, connected generator will generate electricity. So this is actually near seashore, means just it is built on seashore. Sometimes like on shore also it is done, means some 100-200 meter away from the shore also cylindrical oscillating water columns are done, and this type of structure is just on the seashore. So I hope people are able to understand what is the seashore and what is onshore, means just a little bit away from seashore, and offshore is actually a little bit more away from the seashore, like 1 or 2 kilometers away. So I hope this concept is understandable to everyone. Now, based on this, there are many components of this I want to explain actually. So later, because this is my area, so I will now put focus on this. And this is the actual company, which is not company actually, it is actually government supported program in Spain. So this power plant is built there, and the place name is actually Mutriku. So we call it a Mutriku wave power plant based on oscillating water columns. So there are multiple oscillating water columns built over here. And this is the kind of structure. Here we have turbine generator setup, and from this waves strike, and we have rise and fall in the water level over here. And based on that, this system is driven. Now, turbine, because here in this setup, we can see this turbine over here. So one thing we can understand that when there is rise and fall in the water level, so air will be pushed to this side, means outgoing air, and when the water level goes down, when water level goes up, air will be pushed in this direction, means from here you can say left to right, and when water level goes down, it will come from air will come from we can say from right to left. I hope this point is taken. So now we need a turbine which should rotate in only in one direction. If for outgoing air it rotates in, for example, in clockwise direction, or for incoming air it rotates in anti-clockwise direction. So we have no actually meaning it. So net power generated will be zero. Average power generated will be zero. So it won't be of any use. So we need a kind of turbine which is called self-rectifying type turbine. Means self-rectifying here means actually turbine rotates in the same direction irrespective of bidirectional airflow. So here we have a very popular turbine called Wells turbine. Now this turbine is actually made in such a way that blades are made in such a way that it rotates only in one direction. You can see. Hello. Sorry. Some I think Daniel G is asking something. Hello.
Sir, please go ahead.
Okay. Thank you, sir. So here we can see that this the blades are made in such a way that suppose air is coming from, for example, from top to bottom. So this will move in this direction only because one side it is thick, one side it is thin. Now, if air moves from this direction to upward direction, for example, so in that case, irrespective of bidirectional airflow, we can see the turbine will rotate only in one direction. But because here it is converting bidirectional airflow into one direction, so it will also have some problems, and that problem is called stalling problem. So I'll discuss that problem later. Now here we can see what is the advantage of this Wells turbine. First of all, it is simple and it has some better efficiency as compared to other available alternatives, and it can be scaled. It can be a very small as possible, like we can also make it in our lab, a small prototype. It can be made up to megawatt range also. So it is very much scalable. And this is the characteristic of this turbine. Here we can see for these things, with your permission, I'll discuss when I'll discuss the research paper, that we have a plot between torque coefficient, flow coefficient. So here we can see that a torque coefficient goes up for some some values of flow coefficient, but after that it starts decreasing. So we need to maintain all the time flow coefficient at this point or just little below this point. So this is one of the control problem that we can identify from here only, so that we are able to get always maximized power, maximum possible power. Now coming to control techniques. So what are the control techniques available over here? So obviously one technique is actually you see the air column is partially filled. So at the top it has partially filled air. So suppose we have very extreme conditions. So suddenly water level goes up suddenly and down suddenly. So air pressure will also be following that same trend. To access here immediately, so we need to predict first of all that whatever wave is coming, so it's based on its height, it needs to be predicted that the water level is going to be this, and based on that immediately we need some extra valves to release additional air so that the turbine and generator setup operate in a proper range. Otherwise what will happen, it may get damaged, or if it does not get damaged, it may provide some sudden spikes in the power level that may not be good for the grid. So that is why airflow controller is needed at the starting, at the input end only. And rotational speed controllers are actually used to just from the generator side, they are actually operated. So these rotational speed controllers can rotate the speed as per the requirement, so that we are also able to achieve maximum power point. So these are the two techniques which are available here. And so as I have already mentioned that rotational speed control is used for getting optimal operating conditions of Wells turbine in OWC system. And we can see from here also in this diagram that from this side we need some extra valves to regulate the airflow, so that the airflow that is required, maximum airflow, whatever maximum rating it has, turbine has, it should not exceed that. That is one thing. Another objective can also be there, that whatever power we want to generate, so we can restrict airflow in that range, so that whatever extra airflow is there, that is released from this side, so that it does not have additional burden. Rotational speed controllers are obviously from electrical side like this, just to maintain maximum power point. So it may be looking contradictory. Obviously, these two controllers are contradictory to each other. So both these controllers basically need to be complementary to each other. So main objective of this airflow controller should be to just avoid extreme conditions. And for this controller, it should be to get optimized results or maximum possible output power. So, okay, I have already explained all these points, so I would not like to read all these things. Like maximizing the efficiency is one of the objective. Stability, obviously, stable operation, and then protection means overspeeding, all those things. Because if we control the speed as per our requirements, so overspeeding can be avoided during extreme weather conditions. Same thing can also be avoided from airflow control also. And these are the challenges, because the waves have very high variation. So unlike wind energy, where variations are little slow, in wave we have very high variations. So here control challenge is obviously to have very dynamic response. So the controller must be able to respond quickly to sudden changes in the wave conditions. So I have done some studies, some research work. I'll just explain in a little while. Then power quality issue is there in wave energy. Obviously, power quality issue is there because whatever power is generated, it cannot be constant at the just generation end. It needs further processing, and then only it can be connected to grid. So I have done all those real-time studies also. I'll be explaining later. And mechanical wear and tear obviously are there, because when we just vary the speed too frequently based on the wave conditions, so like whatever rotor and all those bearings, all those will get affected much in a very bad way also. It can get affected. So actually very high quality mechanical components are required. Then when we talk about basically for my area, like what technological implementations can be there. So obviously advanced control algorithms are required, like model predictive control or nonlinear controllers, for example, backstepping, sliding mode control, or adaptive controllers, all these things. Power electronics is very much required, high quality power converters, so that they can withstand these high level of fluctuations in generated electrical energy. Then another is airflow controller. Obviously, airflow controller, the main objective is to avoid extreme like here it is written last, overload protection. So this is the must thing for airflow controller. So it should anticipate, and based on anticipation, it should drive the valve, opening and closing of the valves in such a way that excessive airflow should not go to the turbine duct. It should be released through obviously from the valves. But obviously when wave height is very low, so for that we can't do anything. So if the input source is very low, in that case we have to leave it as it is. But the moment it goes very high, that has to be mitigated through this airflow controller. Other things like stability and reliability and maximum energy conversion can also be achieved. But maximum energy conversion, generally based on my experience, we can better achieve through rotational speed controller as compared to airflow controller. These are the challenges. Obviously, response time. Here, the response time is actually very difficult to achieve. The waves which are coming, the height of the wave needs to be predicted in much in advance, like 2-3 seconds in advance, so that means what will be the next peak needs to be predicted, or it should be measured somewhere, like from some distance, so that based on that, the opening or closing of the valve is achieved. So it is very difficult to actually achieve in real time. In theory, we can do anything, but in real time, it is very difficult. So these things are the need of the day, like smart valves and actuators, which can respond faster for precise control. Okay. So I hope I have given a good idea about the area so that all of us are comfortable. If somebody has already idea about the area, it's very nice. But if those who are just seeing for the first time, I hope they have got something. So
Saturday.
Yes. Hello. Okay. So obviously, what the objective of OWC is to just convert wave motion into clean or renewable energy. They use this waste turbine generator to convert. All these things are there. The role of turbine is to convert bidirectional airflow into unidirectional airflow. Then we need control methods to control speed and airflow to get optimized turbine efficiency and optimized output power. Then challenges are obviously very high challenge, high cost is there. Designs are very complex, and the most critical thing is harsh marine conditions. So like we need to be ready for harsh marine conditions like cyclonic conditions, all those things, because how to protect the plant in those unseen conditions, means unfortunate conditions. So these are the very challenging things. Like R&D is very much required in this area for all the aspects. Like my aspect is actually control, but more than control, materials aspect is very much important. The material which are which can withstand actually harsh marine condition is very important. So all these things and pilot projects, all these things, I hope that all these things will lead future improvements and commercialization. So these are the references. If somebody is interested to do some further like exploration in the area, they can actually go and study these references. They will get better idea about the area. Okay, so this is my first part. Now let us move towards the second part of the presentation. Now I'll be actually moving towards one of my recent research paper, which was published in scientific reports. And so the discussion will be of two actually points. First is mathematical overview of OWC plant. Second, how we can design controller. So here we have designed rotational speed controller using neural network backstepping control approach. So why is the need of neural network over here and why we are introducing neural network? I'll be explaining all those things in the due time. So let us first try to understand the mathematics. Maybe if we see this diagram, from this diagram, it looks very complicated. Obviously, if we go for very accurate mathematical modeling, it is very complex. So for a person like me, I have to segregate all the components, and then I have to do the mathematical modeling and then integrate all the components, and then overall from wave to wire, I have to do the analysis. So here we can see, okay, here we can see the first component is obviously waves. So for waves, what is the important thing? The important thing is actually wave height, the wave that is coming. So this wave height is very important. So for that, there are two ways. The simplified way is actually use sinusoidal signals, sinusoidal waves of some period. Generally, the standard is actually standard time period is 10 seconds. So that can be used, but that is very simplified one. If you have visited to seashore or any of the beaches, like in Goa or here in, I was living in Odisha for 7 years, so I mostly visited Puri beach. So you can see that the wave heights are not very much consistent, and also the time period is not consistent. It is very much stochastic in nature. So for that, we need a stochastic model. So fortunately, I did the research in this area and then got many stochastic model like Pearson Moscovich, John Swab, and some M. Cormick, all these people who did a lot of stochastic modeling of sea waves. So how wave height can vary over a period of time, and what is its frequency spectrum, all those things I got. So I used for modeling of this part, I directly used John Swap based. John Swap actually means Joint North Sea Wave Project. It is North Sea is actually in Europe. So for that, they did the modeling. So I used that, and based on that, I just generated the sea waves, wave height signals from this. Now the next component is this chamber model. So what happens actually? I'm just assuming that the wave height over here and the water level movement over here is same. That one assumption I have done over here. So based on that, now what is the input to this? The input to this is actually air velocity, the air that is flowing over here. So this is generated because of this wave height. So we need some relationship between this airflow and this wave height. So for that, I use some reference papers. So wave, obviously, like what is the formula for velocity? Meter per second. Okay. So here, if height is our distance covered in, suppose in seconds. So the distance that is covered in meters in 1 second, that will be air velocity. So whatever wave height waveform I have, if I differentiate it with respect to time, I'll get the air velocity. So that assumption is over there. So in that manner, first this wave model, then second air velocity. Then the Wells turbine has its own established model. Throughout the years, last 20-25 years, many models have, means the mathematical model has been developed. So the where air velocity is given as an input to that. Then turbine model. So turbine will give turbine output as torque. Turbine torque will be the output of the turbine. So torque equation, which is dependent upon the air velocity that is being generated from this side, and also the rotary speed. So the turbine torque is dependent upon two things. So that turbine torque will come over here. Then generator equations. Now generator equations will be dependent upon the kind of generator we are using. So many kinds of types of generator, if we see, you can see permanent magnet type generators or induction type generators. So here in my initial studies, obviously I used DFIG, doubly fed induction generator. So those generator equations can be used. Then some other equations like electromagnetic torque and output power, electrical output power, those equations are also there. So based on that, we can do the full mathematical modeling. So I hope I have explained all the components. Now let us move. So this is the simplified one. Now this is just for representation purpose, that this is known as crest, this is known as trough, and the difference between this crest and trough is known as wave height. This just representation is the sea width. So this distance is called sea depth basically, and other things are there like wavelength, the difference between two peaks or two crests, or from this zero crossing to, or means for a distance for one wave cycle. So this is called wavelength. So all these just parameters are there, but it is very simplified one. If we just use in our research paper this type of model, basically the paper will get rejected immediately. So we need to present some stochastic model over here. Then wave chamber, I have already told you, this is just a proportion, because why we are using this proportion, AOWC divided by A duct. This I have already explained, del by del T, like basically differentiation of height with respect to time gives velocity. But why this proportion? This proportion we can understand from here. Here we can see that this is the OWC cross-sectional area. This is getting converted into this cross-sectional area, A duct. So basically air velocity here will increase because we have less space, less cross-sectional area. Here we have more cross-sectional area. So whatever air flow is over here, it will get converted into more airflow in a proportion of what? AOWC divided by A duct. I hope this point is received. So that is why this proportional ratio is there. So this is our first equation which gives air velocity. And this wave height, we generally, I have already told you that I have generated using John Swap wave model. Now, next, this diagram is already explained, so no need to explain it again. This is torque equation. This is detailed torque equation. Here we can see it is actually a little bit modified. So this flow coefficient, this phi we can see here, this flow coefficient is actually Vx divided by R omega R. So omega R is actually rotary speed and Vx is air velocity. So we can see that this function is dependent upon both rotary speed and air velocity. And this torque is also dependent upon this nonlinear algebraic function. So, and also air velocity is over here. So we can clearly understand that the turbine torque is dependent upon two things, air velocity as well as rotary speed. Now, from here only two control problems are originating. Either we can manipulate air velocity, or we can manipulate what? We can manipulate the rotor speed. So suppose I manipulate air velocity. So if I increase so air velocity is directly proportional to flow coefficient. So I have already shown you the diagram here. Flow coefficient must be below some value. Now that value is for a particular model, it may vary, but for that model it was 0.3 around. So if we want to maintain, and suppose flow coefficient is more than 0.3 and we want to drag it down, so we can reduce the airflow over here by releasing the excess air through air wall. So the airflow that is going to turbine duct will reduce and the flow coefficient will come around 0.3. That is one control problem that we can achieve through airflow controller. Another control problem is actually by manipulating rotor speed. So here we can clearly see it is inversely proportional. So when it is inversely proportional, it simply means that suppose airflow flow coefficient is more, so we need to reduce it to 0.3 level, for example. Then in that case, we need to reduce the speed actually. Increase the speed. So when we increase the speed, the flow coefficient will decrease. So by implementing the rotational speed controller also, we can do this. So basically 0.3 we are assuming to be maximum power point, means as per our current model. So these are the parameters of the turbine. Then we can this flow coefficient diagram, this turbine characteristic diagram is again shown over here, that we need to maintain flow coefficient over here. So if it goes above this, so using both the approaches, we can manipulate it to at this point. Actually, it should not be greater than 0.3. It can be below 0.3, but if it goes too below 0.3, then also it is a problem because the overall power will reduce, generated power. So we need to maintain somewhere here, just below 0.3, means 0.28 or 0.29, like that. So this is one thing. Then coming to generator model. So generator is DFIG type. So here we can obviously we have stator and rotor. So stator will have 3 phase and rotor will also have 3 phases if it is 3-phase DFIG. So but when we talk about controller design, it is very difficult to do in analysis in 3-phase equations. So what is done actually, synchronous rotating frame is actually converted into this it's just a frame referencing. The frame is converted into DQ equivalent. So here we can convert a stator equation into D and Q type stator equations, then D and Q type rotor equations. So ABC is actually converted into DQ. It is also called Park transformation. We can, means those who are have done some study in machines obviously are familiar with this. Then so now we can see that we have many equations, like but we are only concerned about differential equations. How many differential equations we have? This one, this one, this one, this one, and one more equation we need, actually turbine generator coupling equation. So this equation is also important. And all other equations are like this is electromagnetic torque equation, power generator equation. All these are just either linear relationship or just algebraic relationship. So, but the most important relationships are means differential equations, because based on that only we can actually divide means we can derive a model, state space model, and based on that we can go for controller design. So I hope this equation and all these 4 equations are there. So we have 5th order system, and previous equations are not actually differential equations. All these are algebraic equations, nonlinear algebraic equations. For example, this torque equation or any other equation previously. This also is proportional. It is not differential equation, just derivative of wave height gives air velocity. So there is no back relationship. So based on that, we can derive the 5th order system. And now how we can actually derive the controller. So some of the steps I have skipped actually here, like this 5th order system, we convert using a flux oriented control approach to 2nd order system. So just quickly I want to show one research paper so that people will have idea. So this is one of my old research paper which was published in IEEE Transaction of Sustainable Energy. Here you can see that these equations, all these equations we have converted into means we have formulated the control problem. So we converted all these equations using flux oriented control by these assumptions, all these things quickly we can see. And based on that, we converted all these equations into second order equation. So this type of equation means converted, and which in simplified form can be written like this, like in state space form x1 dot x2 dots, where x1 x2 meaning, all these meanings are given over here. These are the states, like omega r is represented by x1 and psi qr is represented by x2 and all other, and these are the meanings. So basically what I'm trying to suggest over here, that this model we are going to use for controller design. So this conversion is given in this research paper. If somebody is interested, can see. Okay. So now coming to the controller design. So first of all, we have designed this neural network backstepping controller. Earlier also, I designed the backstepping controller, but in this paper, actually, I introduced the concept of neural network, because actually this model is very complicated and we are using the simplified model basically. So there are many unknown dynamics of the system. Now we cannot measure those dynamics. We don't have any method to measure those dynamics. So how to compensate for those dynamics? So here my assumption is that those dynamics we can assume to be unknown disturbances. So that we integrate neural network with backstepping controller, and so unknown dynamics will be compensated by neural network. So how we are proceeding for that? So first, we just simply design conventional backstepping controller. We using Lyapunov stability criteria. Obviously, if somebody has done nonlinear control theory, would know. Then after that, when backstepping controller is designed using Lyapunov stability theory, then neural network is integrated into this backstepping controller, and again stability theory is proved. Means we are deriving the backstepping controller law using Lyapunov stability theory, but when we integrate neural network, then again we have to derive, we have to prove that the control law is stable, again using Lyapunov stability theory. This is the most critical part in nonlinear control theory, where we have to prove the stability through established law. Then when these designs are done, so we have now we have done the simulation studies, and then obviously some evaluation and performance comparison is needed. So first thing we have done, we have taken the uncontrolled plant, then uncontrolled plant, then PI is very conventional, so we have taken that from one of the old research paper. Then backstepping from my own previous research paper, then neural network backstepping. Then for all these controllers, we have also optimized the parameters, so that the case of uneven, sometimes it happens that we saw PI controller response intentionally poor. So it should not happen. So we optimized all the parameters, and based on that, we basically did the comparative analysis. So these are some of the highlights, and then outcome is that combined backstepping, Chebyshev neural and PSO optimization yields a robust, adaptive, and MPPT effective control strategy for practical OWC system. So now with this, let us discuss a little bit more about the structure of the controller. So here we can see that suppose this is complete wave to wire model. I have already shown the schematic diagram. So all that diagram, actually, please think that it is inside this block. Here we have wave height. Now this wave height is coming as an input. Now same wave height we need to use actually to anticipate that what should be our reference speed for maximum power point tracking. So same wave height we are also giving some to MPPT block. So if somebody is interested how MPPT block is derived, so again please refer this research paper. Here at the end I have given here at the end, the steps of calculating the reference speed or maximum power point is given. So using these steps, we can, I will also show the simulation that how we are doing this. So this part is there. Then after that, this reference speed goes to the controller. Now here, two types of controller, obviously. Obviously, I think we should also put PI, but because we are not proposing PI controller, we are only doing comparison. So I have not shown here PI, but backstepping and neural network backstepping controller, it goes to that generates actually control command, which is given to this rotor side converter, and based on that the rotor speed is controlled. Also we need some data, states data and this torque data for controller. so that we can calculate all those errors and all those backstepping means whatever is required can be calculated. So I hope this diagram is clear. Then now how we design actually first this simplified state space model that I have already shown in the paper. We considered this, then we convert this model into error model. So this is the error model. So this, if somebody is interested how we are converting this model into error model also, please some of in one of research paper it is given. Then we have this. Now when we convert into error model, this component is very complicated component is coming over here, FD. So like these type of terms are coming. So now if we go in real time, suppose we want to implement something, so it is very difficult to implement this. All these are simplified ones, but this one is very typical. So what I proposed that this FD can be estimated using neural network directly, using system states only. So directly using system states, we estimate this thing. And based on this estimation, we design the controller. So the means requirement of measurement of this component, very complicated component, is avoided. And at the same time, this is actually for known model, but at the same time, if we estimate this one, so some unknown dynamics can also be compensated. So that was my proposal. So we estimated this FD using CNN. So later I will explain how this is happening. Now, this is the control law that we have derived by proving the Lyapunov stability criteria. Now, again, all these steps are very lengthy. So I have already shared the research paper. So I just want to ask Ravin sir if he is present here. Hello. Hello, anyone?
Yes, I am here. Yeah.
Yes, sir. Sir, just I shared one research paper with you.
Yeah.
So on that, actually, all the controller steps were given. So how we can derive? So how we are able to derive this control law? So if the participants have the access to that research paper, they can easily understand that. I can also explain if there is any doubt by directly going to the research paper, that how we are actually designing this control law, backstepping control law over here. So for this state space model, we are designing the backstepping control law. Now, this is the architecture. This architecture is basically derived based on this equation. This equation is actually derived over here. You can see. Now, after that, we introduce the neural network for disturbance term FD. So now, for neural network, we have used Chebyshev neural network. So here in Chebyshev neural network, basically we have designed this type of architecture we have used, where we are considering, because it is just for a smaller component, so we are just considering one layer and two inputs. Basically, two inputs are two states. This is generalized diagram, but two states only are required. So this type of architecture we are using for Chebyshev neural network. And the real equations are like this. So this type of so FD is actually assumed to be this expression. This expression is actually Chebyshev neural network expression. Phi NN is actually the basis function, and this is the Frobenius norm. So this norm is used actually for for the purpose that all the weights are bounded by maximum weight using this norm. And then this is actual FD. Our assumption is that this is actual FD, but its estimation can be like this, because this epsilon we can neglect as an error. So the estimated can be written like this, where this is the actual weight and here it is estimated weight. Then we calculate the FD tilde, which is the difference between actual FD and this FD. And when we do this, so we get this expression. And so this W minus W cap will be W tilde. So we get this and plus epsilon. So this is our neural network architecture that we are introducing in backstepping controller. So here this FD tilde, basically, if we go again back to this, so here we have in our control law, we have one FD over here. This FD term is actually replaced by FD cap, that is estimated using neural network. So this is the difference between a backstepping controller and its estimated version. Now, all these things, after doing all these things, we we write the NN backstepping controller, which looks very similar, only difference is this one. But now when we estimate this FD, we need some training algorithm or training adaptation algorithm, which will actually just modify the weights, neural network weights in real time. So for that, we consider this weight adaptation mechanism, and for that we need to again prove the stability. So again, in the research paper, if you see, the stability is given, all the steps are given. If any confusion is there, I can go line by line and explain all those expressions. If it is required, I can go. But obviously, we have to consider some Lyapunov candidate function, and based on that, we substitute all the values and then do the derivation. And ultimately, we have to prove that the positive definite Lyapunov function means its derivative is negative definite. For a positive definite Lyapunov function candidate, if its derivative is becoming negative definite, then our control law will make the closed loop system stable. So this is the statement that we need to prove all the time. Okay. Now coming back to another important point. So after proving the stability, we have also considered this integral square error type performance index. So this performance index is based only one parameter, that because objective is rotary speed, so the difference between rotary speed is x1 tilde. So 1 tilde squared is called ISE. So now this ISE we are minimizing for all these. PI will have only two values, KP and KI. The backstepping controller will have some constant parameters, so those parameters. Then NNBSC will have some constant backstepping controller parameter as well as neural network parameters. Let me just go back and show you. So here all these parameters like eta and rho, these parameters also are required to be optimized because these will train the neural network. So these also need to be optimized in such a way that the estimation is proper. Otherwise, we will get error. So eta, rho, and some other parameters. These are actually system parameters. No need to optimize. But here we have the sigma 2 and sigma 1. So these two parameters need to be optimized for backstepping, and for neural network backstepping, sigma 1, sigma 2, and eta and rho. So these four parameters needs to be optimized. And for PI controller, obviously KP and KI. So we do that, and this is the overall architecture of NN backstepping. So basically, backstepping, I have already shown the architecture for backstepping. Here we are only estimating this FD, and this FD is estimated over here. And from this block, you can see all these are inputs. Only this is the output FD cap, and it goes to this block, and this gives the U. Please don't get confused by these equation numbers. These equation numbers are taken from this diagram is directly taken from the thesis of my student, because this is part of the thesis of my student Priyanka Nath. So from there I have directly taken the diagram. So that is why these equation numbers are there. But this equation number actually simply mean this law, and this equation number, this actually simply means this law. So basically in this block this is implemented, and in this block this law is implemented. So I hope all these points are okay. Now after that we can go to the simulation result. Now simulation result, when we talk about ocean wave energy, there are or any system, so basically two things are very important. First is uncontrolled plant, and second is controlled plant. So these are the two broader things. Then within the control plant, if we have some previous controllers like PI controllers, backstepping controller, those controller, and whatever we are proposing, so the comparison of all these things are required. So we have done all those things over here. First of all, these are the parameters which are obtained through optimization. So we can see for PI we have this, for backstepping we have this, for neural network backstepping we have sigma 1, sigma 2, rho and eta, and these are the ISE values. Obviously for this we are getting least ISE value, but I'm showing here the neural network backstepping is giving least integral squared error. It does not mean that these controllers are not good. See, this controller is having neural network. Now neural network needs intensive computation. So computation burden is in this controller is increasing, means that also needs to be taken care. So if we have very advanced hardware, then only we can implement this. For like low cost applications, means it may not be possible sometimes that we go for this complicated architecture. We can simply go for PI controller or simple backstepping controller, because here we will need neural network, and that neural network I will show in simulation diagrams also, that you will understand that how it is computationally burdensome. Then these are the waveforms. So this is the wave height generated using this Jones Webb model, and then this is air velocity equation generated. Then this is the flow coefficient for uncontrolled plant. So here you can see sometimes the flow coefficient is exceeding a 0.3 limit. So just for showcasing, and we have taken up to 50 seconds. Then this is the uncontrolled rotor speed, and whatever actually speed is needed, desired for optimum performance, it is not achieving in uncontrolled system. So now we need controller. So the moment we go for controller, these are some other things like turbine torque behavior is like this. So here you can see the torque is getting suddenly reduced in these regions. These regions are these regions where flow coefficient is exceeding 0.3 value. So in these regions, the flow torque is reducing, and these regions are called stalling region. Means stalling region means the turbine is getting suddenly stopped, and the torque is getting reduced suddenly. So that is why it is called stalling. Now this is the generated output power. Here also it is getting restricted to some values, and also these at this point we have some stalling regions. Okay. Now these are the controller comparisons like backstepping, PI, neural network backstepping, and difference. The reference has been generated using MPPT, and then PI, backstepping, all these controllers have been compared. So largely you can see that from larger perspective, all controllers are good. So we have to zoom in and see the actual results. So we can see that the PI is lagging in the speed dynamic response. And here we can see that so this is basically actual rotor speed, then this is the rotor speed error. So in error, actually, we can find more clearer picture that which one is better. So this blue one is actually backstepping, and here in somewhere hidden actually the neural network backstepping, which is more accurate. So that is why it is not very much clear. And the green one is actually PI controller. Now, similarly, this one is actually rotor flux error, because we have two states. For both the states, I have plotted errors for rotor speed also, for rotor flux also. Similarly, we can find here also. This is the control voltage comparison for all. These are the flow coefficients. So here now we can see for all controllers actually flow coefficient is below. So it simply means that we can use all the controllers based irrespective of like accuracy is different thing, but all the controllers are actually fulfilling the normal requirement. That is the one point we should take from here. Now accuracy, if we want to be very highly accurate, then we can go for neural network backstepping. That is a different matter. Now turbine torque gets a little bit maximized on these points. Here also it gets maximized and it goes up to 70, 80, around more than 75 kilowatt range. Then, okay, just one thing I missed. Actually, here I have also taken one criteria called actuator disturbance. So in the first part, I have assumed that there is no actuator disturbance. It is 0. Now, in the next part, I have assumed that there is some actuator disturbance. So for that actuator disturbance, actually, this value we have added to the controller intentionally to see that whether the controller is performing under actuator disturbance or not. So we are able to find that here for backstepping we are getting close to this actual reference value, but it is varying. The PI is varying like this, and neural network backstepping is compensating very fast because it is able to actually adopt the values in between. During the running of the system itself, it is able to adapt. So suddenly it adapts to those values which are able to reduce the error. That is why it is very accurate. Now here also we can see the same thing, and in this also, this is rotor speed error, this is rotor flux error. Then this is control voltage. Here obviously because we have already added the sinusoidal disturbance, so the effect of that sinusoidal disturbance in U is actually seen over here, and these are the flow coefficients. So now we can see that this turbine torque and output power. So now we can see that in terms of utility, it is up to the user which controller to apply. But in terms of accuracy, we can definitely say that the neural network backstepping controller is more suitable. So with this, just some other parameters are given just for understanding. So like these things do come actually not just by us only. Sometimes when we send the research paper to reviewers, so they ask that why this is not there. So based on that, actually this table was added later in the review process. So they asked that please just give the comparison of all these controller in terms of these values. These are the standard time domain parameters like peak overshoot, settling time, and basically for actually without disturbance and with disturbance. So those comparisons are given over here. And we can see that the NN backstepping has less settling time and also less peak overshoot. So with this, I conclude this session. And I have already told you that based on our requirement, we can use. If we want more accuracy, then we can go for neural network backstepping. Otherwise, normal PI or backstepping controller is sufficient. So now these are the references that has been used for this slide. And if time permits, I would now like to go to the simulation results. Directly, I want to go to the MATLAB. So yeah, the same model for that has been used in this paper is actually over here. Is it visible to all of you? Okay. So so here we can see that first of all, this is the overall model. So this is John Swab wave. I have actually so many profiles generated. Ready means I have already generated many profiles of this. You can see here more than 20 profiles are there. So these profiles have been generated using John Swab stochastic model. So these have been taken from workspace to directly to the Simulink model. Now it is coming over here as so this is the wave height which is coming as input to this OWC. Now inside this we have different blocks made in Simulink same as that diagram. So this is the chamber diagram. So here you see wave height is coming and that air velocity is getting calculated and coming as output. I hope this is okay. Then this is the Wells turbine model, and so Wells turbine has two inputs. One is Vx and one is rotary speed. Then output is actually this turbine torque and also flow coefficient, and then also generated turbine power. Okay. Now here we can see that this is the architecture we have just developed. For this, in the slides also we can see, here is the slide, yeah. So basically, these equations are actually implemented over here. Torque equation, this one, and this flow coefficient equation. Power is actually, power is given by just torque into speed. That multiplication is only given for power. So here, the same equations are implemented. So I hope this turbine model is clear. Then this is the generator model. So this is simplified one, but actually we can also use actual model, fifth order model also here we can be used. So now this is the generator model that we are using, and basically it is written in terms of codes. So okay, so these are the codes. So all the parameters, numerical parameters are given over here. Then these are the equations which are given. And then these are the integrators. So if somebody has done the state space modeling, so it is like that. Then based on that, this rotary speed is again given as feedback to the Wells turbine. So, and the torque is coming as an input to this, because we have one turbine generator coupling equation. So torque is coming over here and the speed is going as a feedback. So this overall completes the model. Now in this we have U is actually rotor control voltage. So now this is generated using three controllers. So first, for simulation purpose, obviously we need to give first thing we need to give like this. So this is when we make U0, it is uncontrolled. Uncontrolled means when we run this, okay. So we can see here. Okay, so the same diagram that I was showing over there, some of the values are going above 0.3. So now this is uncontrolled plant. Now we have done the controller design, and also we have calculated the reference speed. So this is the block which is taking airflow velocity as input, and this whole thing is actually giving the and this is basically the MPPT block. So that gives the reference speed. So from this block, we get the reference speed. Now this reference speed, basically X1D, we have put the label X1D as per our paper. So this is coming over here, reference speed. These are the states. So one state is actually this rotor speed, another state is this rotor flux. So these two states are coming to this controller block. Then turbine torque is also coming as another input. Now based on that, inside this, we have these control blocks. Now there are different calculations. We don't have to go in each calculation. First thing, actually we need to understand, I have calculated the errors. Error block is here. So this is the error. So reference is coming and actual rotor speed is coming. So in this block, the error is calculated x1d minus x1. Now this error can be directly used by PI controller, basically not PID. If we go inside this, it is simply PI controller. So if we directly give U to this PID controller, then basically we can remove this part once. We can directly connect over here this, if we can remove this and we can connect this. So this will be simply PI controller. Now if we run this, now PI controller is very simple to implement actually. We don't have need to do these many calculations. So now based on that also we can now calculate this. One second. What is the problem? Okay, sorry. Problem is this one. I need to connect this U now. This U to this control of whatever has been calculated over here has to come over here. So now when I run this, so now I'll get this rotary speed control like this. So this is using basically PI controller. Now all these values are optimized one. Optimization has been done separately. Now we can use backstepping controller. So for backstepping controller, we can see here. First of all, we have two values. Here right now I'm using FD. Basically, I'm calculating FD and FD cap separately. FD cap is actually calculated using neural network CNN, and FD is directly calculated. So here is FD is calculated directly using formula, and so in FD cap we are using directly these values, system parameters, means states. We are not going for this calculation, means based on formula. So this FD cap once we will use. So right now I'm using FD only for backstepping controller. So simply it will be using this one. So this one is simply backstepping controller. So now if I run, so here once again we can see this is now backstepping controller. This is now we can see that it is more accurate. Then we can go for neural network backstepping controller. So now if I replace FD by FD cap, so here FD cap is also getting is the input to this block. So here FD cap is already available, so I can make this FD cap. So now if I run this, now you see, this is the thing I wanted to show. The moment I use neural network, the computation takes time. So why it is taking time? Because it is now computationally intensive. Here you see this block has a lot of complications, like it is very complicated block. All these blocks you can see, and these are all these weights are actually getting trained in real time. You see all these differential equations are there. So means I have used 5 neurons. So for all neurons, basically all the weights, we have to train all these weights separately. So basically fifth order system it is. So based on that, it becomes very burdensome computationally. So now it takes time, but it will give more accurate result. Now obviously you see those diagrams are actually, we save all these diagrams, and based on that we do just paste all the diagrams one after another, and then those diagrams are obtained. So I hope I'm able to give some justification to this FDP. I have tried to show all these things. Now, if any questions are there, I can take up, sir. And also I'm very thankful to Raveen sir and his team for contacting me. And one more thing, just I want to say, these are the research papers. You can go to my Google Scholar account. And this research paper, if you see, if somebody is interested, and I have also published one book in 2021. And if you see this book is very interesting. You see, in this book was written very specifically for those who just want to start the research in this area. So you see, in this book, I have given all these things in detail. These are just introductory parts. Then overview of mathematical model, all these things are there. But the most important thing, these blocks, Simulink blocks are here. So with the help of these blocks also, you can make all these things, these blocks. And if somebody is interested to do more research, you can also contact me, and whatever I can do, I will try to help you out. For all these controllers, I have given the blocks. So, and equations are also given. So those equations you can build inside these blocks similarly. So here, all the Simulink blocks I have given, these blocks. So this book can be found in Springer, and this paper I have already shared. So all other things, if somebody is interested, can be found. So thank you all of you. I had actually really good experience of just explaining these things. I tried in a different way so that it is more receptive in nature. Just presenting the PPT sometimes looks more boring. So that is why I tried something different. Okay, thank you, sir. Please, over to you, sir.
Thank you. Thank you very much. Any questions, participants? Any question if you have, you can write in the chat box, or you can unmute yourself and ask it. Did you get any funding for this project?
Yes, sir. Actually, I had received one funding from DST in 2023. When I was working in KIIT University, sir, as you know that I was recently relieved from KIIT in December, and I have just joined by 1 month back in NIT Silchar.
Okay.
So I was working on a project of the same area. So I developed the hardware. If you want, if you give me some time, sir, I can show you some hardwares also, so which were developed there.
Okay.
1 second, sir. Just quickly, I will show. I have to open my this project file, sir. So here.
It's okay. It's okay.
Move it off, sir. So this is PDF file, sir. I hope this will be understandable. So here, this was the hardware, sir, actually developed. It is very similar to wind energy system. Means in this same system, wind energy setup can also be developed. So this was the setup which was developed using DC motor and PMSG. Now the objective was actually to emulate the behavior of Wells turbine in DC motor. So we actually, I had to close the project little earlier because I had to come to here NIT Silchar. So by that time we did sinusoidal tracking of the torque. Like it was very close to sine waves. Only thing was the difference that we need to do more stochastic, all those analysis, which we will be doing in future in collaboration with my colleagues at KIIT. But at this time, point of time, this was done in lab view. So these are the control panels, all those things. These are the results. So you can see the variation in DC link voltage, very much, all those things. And this active power that is getting generated very much variable in nature. Then our objective was mainly for emulator design. So we were very successfully able to track this, you see this DC motor torque. So reference torque, we had some sinusoidal, and then we were able to track this torque like this. So it gives some sense of like actual Wells turbine like behavior, like the waves like behavior. So incoming waves are coming, they are varying, like it is not perfect, but it can go more stochastic in nature in future. That is our objective. But actually the kind of funding I received, it was just only 15 lakhs. So based on that, all the hardware, where everything was of limited specification. So we cannot stretch it too much. If we stretch it too much, so the hardware will not be able to work. So that is why we, based on our limitations, we try to achieve this one. In that same hardware, we will try to achieve more stochastic nature of this torque tracking, so that we are able to present more more wave-like behavior, means the power generated from actual wave. It was only laboratory setup. So there are many things to be done, sir. In this area, a lot of scope is there, but a lot of hard work is also required.
Okay.
Yes.
Thank
Yes,
you.
sir. Yes, sir.
Thank you very much.
Yes.
Really a wonderful work.
Thank you, sir. Thank you so much.
Any question, participants? You can put in the chat box or you can unmute yourself. Nisha madam, any question?
No, sir. Excellent session, sir. Okay. Thank you so much.
Okay, thank you.
Yeah, I think maybe sessions are in the morning and evening, and now it is closing time. And I can understand. I have also attended many FDPs as participant. So I have missed, sir, I'm very young actually. Just few invited talks I have given. This is my third invited talk. But before that, I have attended many FDPs like all of you are attending. So it is very difficult actually at the end to just ask the question. So I'll just send you, sir. You already know my email ID, sir.
Yes, yes.
And in that email also my Google Scholar link is there.
Yes, yes.
So if somebody is interested, those who can means explore those papers, and also personally contact me. My phone number is also with you. I have shared. So in future, anyone is interested, we can collaborate further also, because I am interested in this area, sir, and the community is means not very much. The research community in this area. So if somebody is interested in working, it would be very good for me also, because I want to increase my community.
Yeah.
Yes, sir.
But very nicely you explained this topic.
Thank you, sir.
Really appreciate it.
Thank you. Thank you so much. Thank you.
So, Merin, if there are no questions, we can go ahead.
Yes, sir. Let's conclude this. Sir, really, we sincerely appreciate Dr. Sunil Kumar Mishra for delivering a dynamic talk. The way complex concepts were connected with the real-world ocean energy application. This made the session extremely valuable for all of us, especially for the new researchers. Your presentations are not only deepened our technical understanding, but it highlighted the research opportunities in this sustainable energy system. So it was truly a pleasure to learn from your expertise. So on behalf of Department of Electrical Engineering of KKWIEER Institute of Engineering, Education and Research and this FDP organizing team and all the participants, we extend our heartfelt thanks for your time, your effort and this meaningful contributions to this program. Thank you so much, sir. Once again, I thank all the participants for your active participation in today's session. Tomorrow, we will have the upcoming sessions. Looking forward your presence, active participation in the upcoming sessions tomorrow. Thank you.
Thank you, madam.
Thank you. Thank you, sir.
Namaste. Namaste, everyone.